All right, guys, so we got to talk about the right-hand rule last time and began to set ourselves up for a transition into Faraday's law. We covered Hans's discovery that changing electric fields produce magnetic fields. Now let's go on to Faraday's law. So, just a few years after Ørsted's discovery, Faraday discovered that just as changing electric fields produce magnetic fields, changing magnetic fields produce electric fields. And this can be exploited to generate electricity. And I cannot underscore how important this is to modern society. Without Faraday's law, I mean, we would probably still have certain forms of energy. Something else probably would have come around. But this is what allows us to use hydroelectric power, wind power, just all kinds of things come from this. And I'll make that clear by the end of this video, just exactly how that works. So, Faraday's law actually says the change in magnetic flux divided by the change in time gives you a voltage, or really an EMF. Change in magnetic flux over change in time gives you voltage. That's really just, delta would technically be a phi. I don't want to get into the letters for this. But if you have a changing magnetic flux, you're going to produce a voltage. And of course, voltage is what pushes charge around a circuit. So you can cause current to flow with this, which is where you get those powerful results. You can generate electricity with this idea. All right, but I made reference to flux, so change in magnetic flux. What is that exactly? Well, flux is the number of field lines, in this case magnetic field lines, going through some area. So you can imagine you've got a magnet, and we could imagine a wire loop. That's our area. How many field lines are going through that loop? That tells you how much flux there is. And that flux changes depending on orientation. So, if your loop is perpendicular to the field, as the first one was that I drew, perpendicular to the field, that gives the most flux. All of those lines are going to make it through that loop. But if you can imagine slowly turning that loop on its side, like this picture, eventually all of the all of the arrows miss the loop. None of them go through the area, and that means that that loop gives zero flux, which I usually try to phrase as a big punchline, and one of my favorite students from the fall semester made me a little sign in my office that says zero flux. If you happen to have seen that, this is why. A perpendicular loop gives the most flux, a parallel loop gives zero flux. That's just like you guys looking at this piece of paper. You can see all of it. If I slowly turn it this way, you can now see essentially zero of it. That is the idea. Well, imagine we do that. If you have a loop in a magnetic field and it's spinning, the flux is always changing. And what did we say Faraday's law tells us? If you have a change in flux, you get a voltage. So, imagine you've got your wire loop, or a paper loop in this case, and I spin it. That area is constantly changing, which means the flux is constantly changing. You might have zero, and then it's increasing until you see the most, and then it's decreasing, increasing, decreasing, increasing, and so on and so forth. As that loop spins, the flux goes back and forth, increasing, decreasing, increasing, decreasing. Well, Faraday's law tells us that that's the voltage. And it turns out voltage does have a sign. It can be positive or negative. So, as we go from increasing to decreasing and back and forth, that's changing the sign of the voltage. And we get that from Faraday's law. Well, if the voltage is changing sign, that changes the sign of the current. And we get that from Ohm's law. Remember, V equals IR. The resistance, that has no directionality. That is purely just how the electricity flows through the wire. But if that voltage is negative, it changes the direction of the current. So the voltage is going back and forth, which means the current flows back and forth, which is alternating current, or the AC from AC/DC. I usually play a little bit of AC/DC on our magnetism mornings because of this. But this is how we get alternating current. Well, of course, if we're going to talk about AC, we have to talk about DC. AC is different from the current generated by a battery, which only flows one direction. Thus, it is called direct current, or DC, and it would just have a fixed voltage at one value that doesn't alternate back and forth, positive and negative. So let's now talk about generators. That's really what we're talking about. What we've discussed here is the setup of a generator. A generator takes mechanical energy, something is causing this loop to spin, and it creates electric energy. Now, that could be something just like you. You could take a crank and spin a loop manually, but you're using mechanical energy and creating electric energy. Or maybe it's on a bigger scale. Maybe it's a huge dam and you're having water flow through some turbines, cause them to spin. Well, they're probably attached to a big loop of wire that's sitting in a bunch of magnets. That produces voltage. Same with the big wind turbines. Anything that can cause something to spin can cause something to produce electric energy. And this understanding, this combination of understanding Hans's discovery and then Faraday's discovery is what has led us to be able to generate electricity. But we can also run this whole thing in reverse. So run this process in reverse and you have an electric motor. So the idea is you stick a loop in that magnetic field. Now instead of turning the loop and producing electricity, you run electricity into the loop. If you flow a current through a loop in a magnetic field, it will begin to spin. There will be a magnetic field created by the current. That magnetic field pushes against the magnetic field that was already there, and it causes this thing to experience a torque. It causes that loop to spin, which is then usually hooked to some exterior item, and then you can cause something else to spin, maybe a tire, a wheel. Thus, a motor takes electric energy and creates mechanical energy. There's a nice sort of symmetry here. A generator takes mechanical energy, creates electric energy, or we could run the whole thing backwards, and it's a motor. We take electric energy and produce mechanical energy. All right, let's see. I've got one last page, and then I'll save one bonus lesson for the end. So generators are where most electricity comes from. But it turns out that alternating current doesn't work for all purposes. For instance, your phone would be fried if you hooked it up to something that was AC. You don't want to fry your phone to a few $100s down the drain. So we've got things that can fix this. A rectifier is a device that takes alternating current and converts it to direct current. And so I've kind of simplified the process into just a couple of steps here, but this is the basic idea. These are plots of voltage versus time. And remember I said the voltage in AC would go positive, then negative, positive, negative, and so on. What we want is just a purely positive voltage. Well, so a rectifier circuit, first it sort of takes the absolute value. It turns all those negative voltages into positive voltages. But that's still quite a bumpy ride. Your voltage goes up and down and up and down and up and down. And that's not going to be good for a lot of electronics either. You can then put some capacitors in there and it helps smooth out those falls. You do that enough times and this becomes an approximately flat line. And you have just one voltage maintained, and that gives you your direct current. We started with alternating voltages, we end with a single voltage. That's the general idea behind a rectifier. And one last object I'd like to discuss is a transformer. And I'm not talking about Optimus Prime here. This is the one that you hook up to the wall and charge your laptop or your cell phone, any number of devices. And what a transformer does is change the amount of voltage. It takes current in from one side, it runs it through a series of these loops. Remember, more loops means more voltage. Well, if this is alternating current, it goes back and forth, it's constantly changing, it produces a magnetic field. The magnetic field then is changing through these loops over here in a second set of coils that has a different number of loops. The different number changes the voltage. You might produce one voltage over here, it then would become a lower voltage. We would step down the voltage if this were real life. But the idea is that you produce a magnetic field with one set of coils, you pick up that magnetic field with another set of coils, the energy is actually transferred through the magnetic field, and then you flow your current out with a new voltage on the other side. But that's the last device I wanted to take some time to describe how it works. Please, if you guys have questions about anything, feel free to reach out to me. I'm going to give one last video to you guys with a little bit of bonus information about magnetism in materials. So we started with that question of how do magnets work, and we talked about changing electric fields. Well, let's figure out where are those electric fields hiding in our little fridge magnets.